molecular orbital theory. So up to now we know how VSEPR theory and valence bond theory can predict the geometry and the hybridization of different molecules. But mm, as I've mentioned, those theories have drawbacks, and so we have scientists came up with another theory called the molecular orbital theory. And here, this theory describes about the formation of molecules as a result of linear linear combination of atomic orbitals. So we know that atoms, they have orbitals, and in quantum mechanics we denote the atomic orbitals by this, as we have discussed in the last chapter, psi. This psi, we know that if we square it, we can know the probability density of probability density probability density. That means this gives us an idea of where the electron may lie. But in for molecular orbitals, atomic orbitals, they combine, they mix up to give us the molecules. Suppose, for example, the atomic orbitals, we suppose, let's say, hydrogen, hydrogen molecule. So hydrogen is made up of two hydrogen atoms. So these two hydrogen atoms, they'll have each one atomic orbital, and then they combine to give us the molecular orbitals. These are atomic orbitals of hydrogen, atomic orbitals. So each of the atom of hydrogen will have one electron each, and this is our molecular orbital. So these two electrons will form a bond, and these are our bonding orbitals, and these are our antibonding orbitals. And if there are electrons left, then it enters the antibonding orbital. Suppose, for example, we'll take helium molecule. So for helium atom has two electrons, helium atom, and then each helium atom will have two electrons. So in the bonding orbital, we'll have two electrons, and the two left over will enter the antibonding orbital. So the bonding orbitals, antibonding. So if we look here, the bonding atoms, the electrons in the bonding orbitals and the electrons in the bonding orbitals are same. That means the bond order, for calculation of bond order, we subtract, for bond order, bond order is equal to half of bonding atoms, bonding electrons minus antibonding electrons. So in case of hydrogen, we have two bonding electrons, so half into two bonding electrons minus zero antibonding electrons. So 2 divided by 2 is 1. That means in hydrogen molecule we have one bond between the two hydrogen atoms. But in case of helium, we have, for the bond order, half into, we have 2 in the bonding orbital, 2 electrons, and 2 in the bonding. So 2 minus 2 is 0. That means we have no bond order. That means this helium, He2 helium molecule does not exist. Helium exists as atoms because it's a noble gas. That's how we predict whether a molecule will exist or not. But as you can see, suppose, for example, if it's helium ion cation, then the atomic orbitals of helium, since this is plus, that means one electron is lost from one of the atom, means two electrons will come in the bonding, in the molecular orbital of the bonding, in the antibonding there will be one electron. So if we check the bond order for this helium ion, bond order is half into 2 minus 1. So 2 minus 1 is 1, so half. Bond order is half. This means that helium ion can exist theoretically because it's not zero. But in case of helium atom, helium molecule, the bond order is 0. That means no bond between the two helium atoms, so helium molecule does not exist. That's how we can prove whether a molecule will exist or not through this molecular orbital theory. Now, suppose we know how to write the electronic configuration of an atom, but for molecule, suppose let's say beryllium. So 1, 2, 3, 4. So beryllium has, the atomic number is 4. That means it has 4 electrons. So for beryllium molecule, it will have 8 electrons. So how do we write the molecular electronic configuration? So we start with sigma 1s and then 2. This is for bonding, and for antibonding, the same. Well, sigma 1s will have an antibonding orbital, so it will have two electrons in that antibonding orbital also. And then we move on to 2s, sigma 2s, 2, and then antibonding, sigma star 2s, 2, 2, 4, 6, 8, so 8 electrons. And then to fill up the molecular orbital, suppose for 1s, beryllium, for beryllium, this is 1s atomic orbital, so it has 2. So this is sigma 1s and this is sigma star 1s. So 2 electrons will enter here and then the other 2 will enter there. And then for 2s, same thing. So this is for 2s. Now here also, if you check this is sigma 2s, sigma star 2s. If you check the bond order, you'll get 0. That means beryllium molecule should not exist. But let's check for carbon. Or for, let's say, before carbon, nitrogen molecule. So nitrogen 7, and then for nitrogen molecule, this it should be 14 electrons. So sigma 1s 2, sigma star 1s 2, sigma 2s 2, sigma star 2s 2, and then we move on to the pi orbitals. So pi 2px, pi 2py, and we'll have 2, 4, 6, 8. It can have 2 to each, so 4 bonding, and then sigma 2pz 2. So if we represent molecular orbital. So for 2s, 1s will be same, so I won't draw it. We'll start drawing from 2s. So this is 2s, 2 electrons each. Sigma 2s, sigma star 2s. And then 2p, that's 3 orbitals each. So 3 orbitals each. So we'll have by 2px, by 2py, and then we'll have another one, sigma 2pz, and then we'll have and the bondings, by star 2px, by star 2py, and then sigma 2pz, sigma star. So how many in the 6 electrons? 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Now if you check the bond order, so the bond order, so here we have how many? 2, 4, 8, 10. So bond order half into the bonding electrons are 2, 4, 8, 10. 10 bonding electrons minus 2, 4. So 4 in the bonding electrons, so 10 minus 4 is 6 over 2, 3. So in nitrogen molecule we have 3 bonds. So nitrogen has 3 bonds. So that's how we can predict the bondings in different molecules through molecular orbital theory. But the catch is there are 2 types of pairing. For nitrogen type of molecules, we adopt these energy levels. But you keep in mind this one. We'll check out oxygen. We'll notice that these 2 energy levels they flip for oxygen type of molecules. So for oxygen type of molecules, let's see for oxygen. So for oxygen is 8, so O2 will have 16. So you try to put the sigma 1s2, sigma star 1s2, sigma 2s2, 2s2, then we have the sigma 2p, sigma 2pz2, and then we have pi 2px, pi 2py, 2, 4, 6, 8, 10, 14, and then we have 2 left. Then we have pi star 2px, pi star 2py. So those 2 electrons, 1 will enter there. Now, as you'll see, in nitrogen type of molecule, this 2pz orbital had a higher energy than this pi 2px and 2py. But in case of oxygen, this has a lower energy. So for 2s, so this is for 2s, 4 electrons in there, sigma 2s, sigma star 2s. And then for 2p, we have 3 here, and we have 3 more here. So we'll have 2pz, sigma 2pz has a lower energy, and then the other 2 by 2px, by 2py, and then we have the pi star 2px, pi star 2py, and then sigma 2p z star, then the bonding. So 8 electrons. 1, 2, 3, 4, 5, 6, 7, and 8. So 1, 2, 3, 4, 5, 6, 7, and 8. So it is corresponding to this, to the molecular electron configuration. Now, if we check the bond order, how many bonding electrons? 2, 4, 6, 10. So we have 10 bonding electrons minus 2, 4, 6. 6 antibonding electrons. So 4 over 2 is 2. So oxygen molecule has two bonds between them. So that's how we can calculate or the bond order as well as how many bonds are present between two different molecules for that matter. So for your practice, you can check into O2 minus the bond order as well as the molecular orbital diagram, even carbon monoxide, and then yeah, oxygen. So this is another assignment. So some of you haven't submitted the assignment. I've recorded the roll numbers. So you pay attention to your assignments because this year your internal marks, from your internal marks there are 7 marks from your assignments and your project works. So I suggest you take note of it, and I expect it before Sunday to my number. So we'll start with another chapter in the next video. Let me check which chapter. Yeah, we'll be starting states of matter. States of matter. So you can also go through the chapter and we'll meet.